frees the universe a heartbeat after the beginning. No planets, no oceans, only darkness and drifting dust. Now press play. Gravity squeezes a cloud, a star ignites, and a blazing disk spins up around it. Inside that maelstrom, specks of dust collide, stick, and snowball until one world emerges from fire. This is how Earth began, not with a whisper, but with impacts so fierce they forged a planet. About 4.6 billion years ago, the young sun was wrapped in a protoplanetary disk, gas and mineral grains orbiting like a flattened storm. Turbulence stirred the mix. Electrostatic forces made tiny grains cling, forming pebbles, then boulders. With each collision, momentum glued raw materials together, turning a dusty swirl into a construction site for worlds. Once bodies reached kilometers across, gravity took over. Bigger meant hungrier. Larger objects pulled in more debris, growing even faster in a feedback loop called runaway growth. Soon, Mars-sized protoplanets prowled their orbits, sweeping, smashing, and merging. Every impact released colossal heat, melting rock and reshaping surfaces. In the packed early solar system, a Mars-sized body, Theia, struck the proto-Earth a glancing blow. Rock vaporized. A ring of incandescent debris encircled Earth, and within a geological blink, that ring coalesced into the Moon. The collision altered Earth's spin and tilt, and mixed materials from both bodies, signatures still recorded in lunar and terrestrial chemistry and angular momentum today. After the impact, Earth was an ocean of magma. In that molten state, the planet differentiated. Dense iron and nickel sank to form the core. Lighter silicates rose to build the mantle and a thin, cooling crust. This separation locked in Earth's layered architecture and primed its internal engine, the flow of heat that still powers volcanism and plate motion. In the liquid outer core, churning metal plus Earth rotation generated a geodynamo, a global magnetic field. Invisible lines wrapped the planet, deflecting charged particles from the sun. With this shield, Earth could better retain atmosphere and surface water against the erosive solar wind, a crucial step toward long-term habitability. Volcanoes exhaled steam, carbon dioxide, nitrogen, and sulfur gases from Earth's interior. Water-rich asteroids and comets added more volatiles. The earliest air lacked oxygen. It was a greenhouse blend dominated by CO2 and water vapor. This breath from below seeded clouds, rain, and a climate engine capable of balancing a faint young sun. As impacts eased and heat radiated to space, the crust cooled. Water vapor condensed into clouds. Then rain fell, perhaps for millennia, pooling into basins to form the first long-lived oceans. Greenhouse warming offset the dimmer sun, keeping water liquid and the surface stable enough for chemistry to persist. In a few 100 million years, dust became a world with a layered interior, a magnetic umbrella, an atmosphere and oceans. Next, how the moon steadied Earth's tilt, how plates began to move, and how sky and sea learned to regulate a fragile, habitable climate.
Earth now had layers, a magnetic shield, and oceans, but stability would decide its fate. The moon, moving plates, and a self-tuning sky turned a violent newborn into a planet that could endure. The moon's gravity stabilized Earth's axial tilt, reducing chaotic swings and seasons that can devastate climate stability over geologic time. Its tidal pole also amplified early tides, mixing shallow seas, stirring coastlines, and establishing daily and monthly rhythms across the planet. A steadier tilt means more predictable seasonality. Stronger tides mean energy delivered to shorelines and shelves where rock, water, and dissolved chemicals interacted at scale. These repeating cycles became the metronome for a stable surface environment. As Earth cooled, a basaltic crust thickened over a convecting mantle. Heat escaping from the interior drove slow, rolling currents of rock beneath the surface. Where mantle rose, it split crust and created new seafloor. Where plates collided, one slid beneath the other and returned to the mantle. This is plate tectonics, Earth's long-term heat exhaust and surface-shaping engine. Plate tectonics built mountain belts, carved ocean basins, and recycled materials between the deep Earth and the surface. By constantly refreshing crust, it maintained chemical gradients and habitats, and it helped keep the carbon cycle running for billions of years. Fresh volcanic rocks react with rainwater and carbon dioxide, breaking down to form dissolved ions that rivers carry to the sea. There, carbon can be locked into carbonate minerals and buried in sediments. When climate warms, chemical weathering accelerates, drawing down more CO2 and cooling the planet. When climate cools, weathering slows, allowing CO2 to build back up. This negative feedback, rock weathering balanced against volcanic and seafloor CO2 sources, acts like a planetary thermostat, keeping oceans liquid even under a fainter young sun. It is one reason Earth remained temperate while sister worlds veered toward extremes. The air blanketing early Earth held almost no oxygen. Instead, carbon dioxide, nitrogen, and water vapor dominated, with trace sulfur gases. Volcanic outgassing and reactions with fresh rock set the baseline, while ocean chemistry buffered swings in acidity. The result was a thick but workable greenhouse that limited freezing without boiling the seas. Clouds formed from evaporated seawater returned rain to continents. Rivers returned dissolved materials to oceans, and the cycle closed, moving heat, water, and elements around the globe in enduring loops. Oceans are more than water. They are heat batteries and chemical reactors. Currents moved warmth from equator to poles, moderating extremes. Seawater absorbed and released CO2, while sediments stored it for the long term. The hydrologic cycle, evaporation, condensation, precipitation, runoff, became a heartbeat that smoothed climate shocks. Tides, winds, and currents kept coastlines dynamic, mixing nutrients and maintaining chemical gradients across shelves and shallow seas, key interfaces between rock and water that persisted for eons. Buoyant continental fragments, enriched in lighter minerals, resisted recycling compared with basaltic seafloor. Over time, collisions stitched fragments together, thickening and raising continents above sea level. Land altered weathering rates, river systems, and nutrient delivery, feeding the carbon cycle and sculpting climate on million-year scales. Continental shelves, broad shallow seas fringing land, became vast chemical workspaces where sediments accumulated and carbonates formed, locking away carbon and stabilizing the atmosphere. Ancient zircons carry oxygen isotope signatures showing liquid water existed surprisingly early, within the first few 100 million years. Lunar rocks preserve evidence of the moon forming impact and its timing, while meteorites capture the chemistry of the solar system's building blocks. Together, they mapped a rapid sequence: accretion, differentiation, impact, oceans. These archives reveal a planet that moved from magma to water with astonishing speed, not instantly calm, but increasingly regulated by deep, repeating cycles. The moon steadied Earth's tilt, plates vented heat and recycled rock, the carbon cycle tuned climate, and oceans moderated extremes. Stability didn't mean stasis, it meant reliable cycles and abundant interfaces where water, rock, and gases could interact. In the final act, these planetary systems sustain a home for billions of years, while hinting at how worlds like ours might arise elsewhere. Next, how Earth's deep engine, hydrosphere, and atmosphere kept this balance over deep time. With the moon-stabilized tilt, moving plates, oceans, and a tunable sky, Earth now had to do one more thing to survive billions of years. Keep its cycles running so water stayed liquid, climate stayed temperate, and the surface kept renewing. Oceans acted as heat reservoirs that absorbed solar energy and released it slowly, smoothing day-night and seasonal extremes across latitudes. Evaporation, condensation, and precipitation formed a closed hydrologic loop that transported heat and chemicals from sea to sky to land and back again, maintaining long-lived bodies of liquid water. Early air, dominated by CO2, N2, and water vapor, interacted constantly with rocks and oceans, which buffered acidity and gradually drew down carbon into sediments and crust. Volcanic degassing and seafloor processes returned carbon to the atmosphere over geologic time, sustaining a slow exchange that prevented permanent snowball or runaway greenhouse states under a changing sun. Chemical weathering of fresh basalt and continental rocks consumed atmospheric CO2 and delivered ions to the ocean where they formed carbonates that were buried and stored. Because weathering accelerates in warmth and slows in cold, this feedback stabilized climate around the liquid water range, despite the faint young sun, acting as a planetary thermostat. Plate tectonics recycled crust through subduction, metamorphism, and volcanism, renewing surfaces and sustaining nutrient and redox gradients vital to long-term surface chemistry. Water carried into subduction zones lowered mantle melting points, fueling arc volcanism that built and thickened buoyant continental crust, creating durable land masses and broad, shallow shelves. By damping chaotic tilt variations, the moon reduced extreme climate swings, while tides mixed shelf seas and influenced coastal sedimentation and nutrient fluxes over daily to monthly cycles. Over time, the moon slowly receded, lengthening Earth's day and subtly evolving tidal energy. Yet its stabilizing effect on axial tilt persisted as a background control on climate. The geodynamo in the liquid outer core created a magnetic shield that helped deflect solar wind, limiting atmospheric sputtering and escape of light gases. By curbing long-term erosion of the upper atmosphere, the field improved the odds that surface water and air could persist across billions of years of solar activity. Ancient zircons indicate liquid water existed within a few 100 million years after Earth formed, implying rapid cooling and early oceans. Lunar samples and dynamics support a moon born from a giant impact, while meteorites preserve the chemistry of early solar system material, anchoring the sequence from accretion to differentiation to ocean formation. Earth's unique combination, moderate mass and orbit, early ocean formation, persistent plate tectonics, a long-lived geodynamo, and a large stabilizing moon stack the deck toward climate stability. These planetary systems created abundant, repeated interfaces where rock, water, and gases could cycle, making Earth resilient to shocks that drove neighboring worlds toward extremes. Earth's origin is a chain, not a single spark. Dust to planetesimals, protoplanets to giant impact, magma oceans to layered interior, outgassing to oceans, plates, field, moon, and carbon cycle to a long-term home. With this foundation in place, life could later transform the air and surface, but the planet's survival machinery was already running, quiet, patient, and powerful.